Okay, when we're talking about optimization in calculus, we're going to give in some type of a situation, usually geometric, with either an area. Okay, let me get my area, right? We're going to talk about an area. What thing gives you the biggest area or the smallest area, depending on how you want to optimize it? Or what are the dimensions that will give you the greatest or the smallest volume? Okay. Now, as both of these are geometrical ideas, I hope you remember all, or if not most, of your geometric formulas for like volume of things like three-dimensional objects, cylinders, and or cubes or prisms and things of that nature. Okay. But there are a couple of things that we have to do in order to be able to do these problems. So first, we're going to talk about some things that you have to show. So after we read the problem, what are we trying to optimize? Is it the area? Is it a volume? Is it a distance between 2 points? Okay, what is it that we're actually trying to optimize? Okay, question number 2. Okay, we have to define the variables. Is it x and y? Is it L and W? Okay, what are we going to use in our formula in order to make sense of our problem? Okay, number 3, what is the primary equation? Okay, so is it volume of a cube, right? How many variables do we have in these formulas? Is it the perimeter, right? What kind of things are we talking about that we're going to be optimizing in your problem? Okay, so what's the primary equation? Now the next question is similar. What is the secondary equation that relates your variables? Because chances are in your primary equation you're going to have 2 variables, like an x and a y. Okay, we don't want to differentiate when we have 2 variables because then you have to do it implicitly, and Lord knows that that's kind of difficult sometimes. Okay, so we're going to use our secondary equation to solve and substitute so that our primary equation only has 1 variable in it. Okay, and once we do that, we're going to differentiate and figure out where that maximum and minimum point is. Okay, so these are our steps that we need to think about as we're doing optimization problems. So let's look at a couple and how that works. So here's our first example. We're going to find some random point on the graph of this equation. Right? This is a square root equation. So hopefully you have some kind of a knowledge of what that looks like without graphing it. Well, you might have to graph it. That's okay. I have a knowledge, so I'm going to show you in a minute what it looks like. So that is closest to this point, right? So we want to figure out the distance that is the smallest. Okay? The distance that is the smallest. So that's our goal. Okay? So let's see, what does this even look like? Root of negative x plus 8. So this would be, if I rearrange my parentheses a little bit, this is the square root of negative x minus 8. So hopefully you know this graph, the square root moves 8 units to the right, but then opens to the left because it is a negative. So here's some of our pre-calculus, your algebra 2 transformations. So we're going to move 8 units to the right. Okay, that's where it touches, right? That's its maximum domain because it opens to the left. Now talk about our square roots. If we go square root of 1, that's going to be 1. Square root of 4 is 2. Square root of 9 is 3. So we're just putting some points on here, right? You could plug them in and it would give you the same answer. But this is the graph of negative x plus 8. Root negative x plus 8. Okay, more or less, right? It's just a sketch. It's not perfect. I'm not using a calculating device. And here we have the point 2, 0. So we want to know, right, what point is closest to this point, right? What point on the graph is closest to our point 2, 0? Right? So we can draw lines and you can get out your ruler and we can guess all day long, but let's use math. It's much more precise. Okay? So what we're basically looking for is distance, right? We have a distance formula for that. So if you remember the distance formula, that looks a lot like this. So there's our distance formula. Okay, one of these points, x1, y1, is going to be our 2, 0, right? That's our fixed one. That's not going to change. These other ones, right, are going to change. Okay, so let's see, what do we know? We know that x1, let's call x1 2. Okay, and we don't know the x sub 2, right? That's what we're trying to find. Yeah, the coordinates of this point that are going to be the closest. So they have an x value plus the y value for our point is 0. That's excellent. And what is the y value of this point? Okay, that y value is always given to you by this equation. Okay, we don't know exactly where the x is, but we do know what the y value is in terms of x. Remember, we can only have one variable in your equation. So that would be, let's see, roots negative x plus 8. That's your second y point, and we're going to square that. Okay, so now you have your algebra that we're going to have to solve this equation for x. Okay, so let's see what we can do to simplify this a little bit before we get too crazy. So this is our distance equation that we want to find the minimum value for. Okay, remember the minimum is going to be the bottom of a quadratic where we have a slope of 0, right? Horizontal tangent line. So we're going to take the derivative and do a sign analysis to see where it changes to a minimum. Okay, so that would mean that the graph is decreasing on the left and increasing on the right, right? That gives us a minimum value from your graph. If we know the derivatives, right, we know the slopes. If the slopes are decreasing and then the slopes are increasing, that means we had a bottom of our graph. So that's going to be our minimum. So that's what we're looking for. So let's take the derivative of this root right here. Okay, so it might help if we change this into radical form, take it from radical form and change it into power form. Okay, or if you love taking the derivative of roots, take the derivative of a root. It's okay with me, whichever way you do it. Okay, so taking it and raising it to the 1/2 power. Okay, d prime, this is a product rule differentiation. Okay, the 1/2 comes to the front, and we leave the parentheses alone. Okay, we raise it to the 1 less power, so this means the negative 1/2 times the derivative of our parentheses, right? This is a chain rule, so what's the derivative of x squared minus 5x plus 12? 2x minus 5. Okay, I guess we can do a little bit of simplifying if we want. And we can put the denominator of 2x minus 5, right? That's the denominator, or rather the numerator. That's your stuff on top. Okay, oops, undo that. We had a 1/2, so that's a 2 in the denominator. Right, this is the square roots. This negative 1/2 becomes a square root in your denominator. X squared minus 5x plus 12. Okay, so what do we want to know about this function? We want to know when the slope is equal to 0. Right, that's what gives us your horizontal tangent line. Like I said up here, you have to have a horizontal tangent, which means you have a slope of 0. Derivative equals 0. Okay, so how do we solve this equation for x? Cross multiply, right? So when we cross multiply, we basically get 1 times the numerator and the denominator times 0. So yes, the numerator comes out to equal 0. So 2x equals 5. So x equals 2.5, or 5/2 if you want to write it as a fraction. It's okay with me either way. So if we come over here and we do a sign analysis at 2.5, okay, we plug in a number less than 2.5. Okay, so if you plug in a number less than 2.5, like say 1 or 0, right? 2 times 0 is 0. 0 minus 5 is a negative value. So the left of 2.5 is negative. And what if we plugged in a number bigger than, like say 3, 2 times 3 is 6, 6 minus 5 is a positive. So sure enough, your slopes change from negative to positive, which means this is in fact going to be your minimum value. Okay, so we have a minimum value when x equals 2.5. So our last thing to do is, what is the y value? When x is 2.5, what is the y value that corresponds to it? Since we want the point. So remember, the y, or f of x, is the square root of negative x plus 8. Yes, from our equation, the y is the negative of the root of negative x plus 8, which is, let's see, 8 minus 2.5 is 5.5. Okay. So have we found the point on the graph that's the closest to it? I believe so. And that point is at 2.5, comma, square root of 5.5, right? Which is something a little bit bigger than 2, but smaller than 3. And I would agree that somewhere in here maybe is going to be that closest point. Okay, yes, sometimes there's a lot of algebra and there's some thinking involved, but you can do it. You're good enough, you're smart enough, and doggone it, math is figure-outable. Okay? All right, optimization. Let's look at another example, shall we? Sure, let me pull one up. Okay, in this problem, we're trying to find the dimensions that will make this rectangle the biggest. Okay, this rectangle is the biggest. What is the biggest area that could possibly make? Okay, so once again, this is a rectangle. The dimensions of your rectangle for the area are the length times the width. Okay, length times width. So the length here from 0 to point D is x units. And because of symmetry, the length from 0 to point A is also x units. So the whole entire length of my rectangle is 2x units. Okay? It's important to be able to label your variables so that you don't have as many fractions as possible. Okay? Try to use whole numbers and multiply if you can. And then the height is, of course, the y value. Okay? The height of this rectangle is the y value. So if we want to maximize area, the area of the rectangle, that's the maximum. Area is the length, which is 2x, times the width, which is y. Okay, so that's the formula that we want to maximize. And hopefully you all notice that there's an issue here that we have two variables. Okay, so we're going to try and eliminate that y because I know an equation that I can put in there instead of y, so that I only have one variable. Okay, sometimes this is the hardest part of the equation, or this whole entire process, is figuring out what the formula is. Okay, so I'm replacing y with the given equation from our problem, so now I have one variable in my formula. Okay, so I have the area equals negative 8x cubed plus 8x. And this is the equation that I want to try and maximize. Okay, I want to maximize this equation. So let's take the derivative and see what happens. Okay, so once again, we're going to take the derivative and we want to maximize it. So we want to have increasing values on the left, so positive slopes on the left. And we want to have decreasing values or negative slopes on the right. Okay, so we're going to find that point, right, that critical point, and we're going to do a sign analysis to see which one gives us a maximum value. Okay, so hopefully this is a fairly easy thing for you to derive. A prime, right, A prime is the derivative of our area, equals, let's see, this is negative 24x to the second power plus 8. Negative 24x squared plus 8 is the derivative of negative 8x cubed plus 8x. And if we're trying to find the slope of 0, you take your A prime, and we want to know when is that slope 0, right? Because it's going to be a horizontal tangent line, and a horizontal tangent line has a slope of 0. So we set this equation equal to 0, and we solve. Okay, so hopefully solving this is not a problem for all of you amazing brainiacs. X squared equals 1/3, right? When you divide both sides by 24. Divide both sides by 24. And then taking the square root, we get root of 1/3. Okay, and I'm sure there's lots of ways that you could simplify that with rationalizations and stuff. But let's just go ahead and leave it alone. It really doesn't make that big of a difference. So the x value is 1/3. Let's verify that that's going to give us our roots, I guess root 1/3. Okay, so what's a number less than root 1/3? How about 0? Definitely 0 is less than root 1/3. Anything 0 is less than a positive. So if you plug in 0 here, we get, we get 0. That's not very good. Let's think of something else. How about -2? Right, is that less than positive 1/3?
Yeah.
Okay, so -2 cubed is -8. -8 times 8 is 64. Okay, so I'm plugging into this equation. 64 goes there. No, over here, right? I'm plugging in negative.
To the prime or to the regular?
Plugging into prime.
Like that's a prime.
That's where we're going. We're going into there. So we can use 0. It's all right. I went to the wrong equation. Let's use 0. Yes, if you plug in 0, we get a positive 8. Excellent. Plug in 0, we get positive 8. And what if we plug in 1? 1 is a number greater than root 1/3. If you plug in 1, we get -24 plus 8. So sure enough, it's negative on the right and positive on the left. So this is in fact going to be our maximum x value. The maximum occurs when x is root 1/3. Okay, so what is that y value when x is root 1/3? Well, there's a formula for that. Y equals -4 times x squared plus 4, right? That was our formula from up here. -4x squared plus 4. Okay. -4 times 1/3, because that's what happens when we square a radical, is -4/3 plus 4. 4 as thirds is 12/3. Yes? So -4/3 plus 12/3 is positive 8/3. Okay, so to answer the question, the points or the coordinate that will maximize our area is root 1/3 and 8/3. Okay, so this is the point that will maximize our area. Now, if we cared what that area was, you could plug that into your formula and figure it out. But we don't really find, we just find the x and the y coordinates so that it is a maximum. Okay, so this is how optimization works. You take your formulas, you write it as one variable, you take the derivative of that, and you figure out when it's a max or a min, depending on whether you want to maximize or minimize.